Okay guys, I wanted to do another quick little video here on this last section of the acid-base chapter. So this deals with acid-base titrations, and I wanted to go over a few key points of those. Again, this is a section where the problems are a bit involved, and so I'll be skipping most of the details, but I did want to show you a few key points. So this first slide here is really just meant to remind you that acids and bases neutralize one another. And in this case, we're talking about strong acids and strong bases. And so what I've presented you here with is a molecular equation for the neutralization of sodium hydroxide with hydrochloric acid. And so proton is donated to the hydroxide. That makes water, and it leaves behind sodium chloride in aqueous solution. Recall from Chem 120 the topic of generating net ionic equations from a molecular equation. So what you do is you take the strong electrolytes and you break them up into their ions. So HCl becomes H plus and chloride. Sodium hydroxide, you get the sodium cation. I missed a plus sign here, but then you'd have plus hydroxide. Water, of course, you leave in its molecular form, and then the strong electrolyte sodium chloride also gets broken up into its ions. And you can cancel out the spectator ions, that is the ions that appear on both sides. So the chloride appears on both sides, and the sodium appears on both sides, and you can cancel those out to give you the so-called net ionic equation. And all strong acids and bases, when they react together, they all have the same net ionic equation. That is, I could have used hydrobromic acid or hydroiodic acid. I could have used lithium hydroxide or potassium hydroxide. It doesn't really matter. As long as it's a strong acid and a strong base, you're always going to wind up with the same net ionic equation, which involves the formation of water. So on to the subject of titration curves. So a titration curve, what it does is it shows the pH of a solution, say in this case an acidic solution, as you slowly add sodium hydroxide. So here you would use a beaker or an Erlenmeyer flask to hold your acid solution. And then you would use a burette, that's that long, narrow cylinder, which allows you to deliver a specific volume of another reagent, in this case, a base, sodium hydroxide. So we are adding sodium hydroxide to, in this example, a hydrochloric acid solution. And so we've got 25 mils of 0.1 molar HCl in the receiving flask, and then we are titrating that with 0.1 molar sodium hydroxide solution. Okay, and so you can imagine adding a little bit of sodium hydroxide and then measuring the pH of the solution. And this is the type of curve you would see as you add a whole bunch of sodium hydroxide. I wanted to point out a specific part of the titration curve called the equivalence point. That's the point in the titration where you have added, in this example, a stoichiometric amount of base to the acid. And for this example, since the concentration of the acid and the concentration of the base are the same, the equivalence point occurs when the volume of the base added equals the volume of the acid in the receiving flask. And so that's at 25 milliliters. And you see what you get at the equivalence point for a strong acid, strong base, you get a pH of 7. So when you titrate a strong acid with a strong base, or vice versa, at the equivalence point, the pH of the solution is neutral. It's equivalent to the pH of neutral water. We'll see a counterexample a little bit later. It's a little bit different when you titrate a weak acid with a strong base or a weak base with a strong acid. There, the equivalence point, the pH is not 7, it's something else. And so we'll talk about that. That's one of the points I wanted to mention. Anyway, we'll deal with this strong acid, strong base titration curve first. This is a typical problem where you're doing acid-base neutralization. These problems can be quite tedious, and so for the most part, they are not going to be part of our assessments. However, I did want to say a few words about the titration problem. So in this problem, again, you've got, it's just like the figure we looked at. You've got 25 milliliters of the strong acid, 0.1 molar, and you're titrating it with 0.1 molar sodium hydroxide. And what they want you to do is to calculate the points along the titration curve. So calculate the pH when you've added 0 milliliters of base, when you've added 12.5 milliliters of base, 25, and 37.5. So just let me go back to the figure here. At different volumes of base, they want you to calculate the value of the curve. That's the point of this problem. Well, the first point is rather easy. Since it's a strong acid, it completely dissociates. You know the concentration of the acid, therefore you know the concentration of the hydronium, and so you just take minus the log of the hydronium concentration to give you a pH of 1 in this case. Now, when you've added a little bit of base, what's going to happen is that sodium hydroxide is going to consume some of your HCl. It's going to consume some of your hydronium. And so in order to calculate the pH, you need to take into account two things. You need to take into account the fact that some of the hydronium has reacted with the sodium hydroxide, so it's gone. So that's going to decrease the concentration of the hydronium. But you also have to take into account the fact that you have added two volumes together. You've added 12.5 milliliters of base to 25 milliliters of acid. And what that's going to do is it's going to throw off your concentrations. So you're going to need to recalculate them. And that's what's going on in this formula. So you're taking into account the fact that the number of moles of hydronium initially has decreased because some of it has been consumed by the hydroxide. And then you're also taking into account the fact that the volume is not the same as it was before. It is now the volume of the acid that you had plus the volume of the base that you've added. Okay, and so you work through the details and you wind up with a pH that is now slightly greater than the pH that you started with. As you'd expect, if you neutralized some of the acid, you would get a less acidic solution. We'll just move on here to part C and part D. In part C, this actually is the equivalence point, and you can actually eyeball that because you know that you've got 25 mils of 0.1 molar acid, and so if you've got 0.1 molar base, then the equivalence point is going to be at 25 mils. And so here, the pH is going to be 7 because you have a pure water solution. In part D, you've added more moles of base than you had of acid originally, and so you're going to wind up with a basic solution. And what you need to do is to calculate the amount of leftover hydroxide, so the excess hydroxide in the problem. And it's the technique is the same as before, only instead of hydronium being the limiting reagent, now, or well, in this case, hydronium is the limiting reagent. In the previous case of the part B, the hydroxide was the limiting reagent. And anyway, in the end, you wind up with a basic solution. Here's an example problem if you want to work through it. What I wanted to do next was to talk about the titration of a weak acid with a strong base. And I'll point out the feature here that the pH of the equivalence point for titrating a weak acid with a strong base, we see that it's a slightly basic solution, whereas for a strong acid, strong base, it's neutral. And the question is, why does that occur? Well, the reason it occurs is because when you form the conjugate base of the acid that you're titrating, it undergoes hydrolysis. So you're adding hydroxide to your weak acid. And in the course of neutralizing that acid, you form its conjugate base. So let's suppose that you have reached the equivalence point, that is, for every mole of weak acid that you have added some hydroxide. So there's no extra hydroxide in the solution. It's all been consumed by the weak acid. However, you have this conjugate base, which is in fact somewhat strong because the corresponding acid is weak. So this is a fairly strong base. It's capable of hydrolyzing water. It pulls a proton from water that reforms a little bit of the acid, and it also makes the solution slightly basic. So if I go back to the picture, when you titrate a weak acid with a strong base, at the equivalence point, the solution is slightly basic due to the hydrolysis of the acid's conjugate base. And if you try to titrate a weak base with a strong acid, you get the opposite. You get a slightly acidic solution at the equivalence point due to the hydrolysis of the conjugate acid now. So these titration problems, again, are quite involved. Even the part A, where you haven't added any base to the weak acid, is somewhat complicated because it's a weak acid, and so you have to use the techniques that we've looked at before. You know, you could go through an ice table, calculate the hydronium concentration, and then calculate the pH from that. Oops. Yeah. When you've added a little bit of base to the weak acid, what results is a solution that has a significant amount of the weak acid left over, plus a significant amount of the conjugate base. From the last video, we learned that that makes a buffer solution. So when you want to calculate the pH for part B, you have to treat it as if it were a buffer and use the Henderson-Hasselbalch equation. And these two calculations here, which are somewhat involved, are where you're calculating the concentration of the conjugate base and the leftover weak acid. Once you have those numbers, you just use the Henderson-Hasselbalch equation and you get the pH of that buffer, which in this case is 4.74. Here at the equivalence point, you now have a hydrolysis problem, and so you have to work the hydrolysis problem as a weak base. And so you calculate what's going to be the initial concentration of of the conjugate base, the acetate in this case, and then you work a Kb problem trying to find the hydroxide concentration, and then you calculate the pH from the pOH. In this case, you get 8.72 as the answer. This part is a little bit easier. Once you have passed the equivalence point, now you have a basic solution. You just have to figure out how much excess hydroxide you have. Once you get that concentration, you then just take 14 minus the pOH, and you get a basic solution. So if you look in this graphic here, by the time you've gotten to, where you've fully saturated the solution here with base, notice that the pH of these 2 points beyond the equivalence point, they're both the same. So you have a basic solution in both cases. Anyway, that's all I wanted to tell you about for this video. There's a small section here on acid-base indicators, but it's not high priority material, so you can omit that if you wish. So I'll stop it here.